This is episode 247 of the Space Nuts podcast, and Andrew Dunkley here with Fred Watson. And a big shout out to our patrons, the people who put a little bit of money every month into the kitty to feed Fred's cat and to keep the website running, things like that. We thank you from the bottom of our hearts that you think we are worthy of a few dollars. If you would like to become a patron, just go to our website, spacenutspodcast.com, and click on the subscribe button. It's up on the top right hand corner, whichever one that is, because I'm facing a camera and it could all be reversed. I have no idea. But you can click on there and see what options are available to you. You can subscribe to package deals, which gives you 2 or 3 podcasts depending on what you want to do. Or you can just make a one-off donation, or you can become a patron through Patreon or through Supercast. What we're ultimately aiming to do is to make the podcast 100% reliant on listeners only. And that means getting as many patrons as we can, and it's good to see a few more have signed up in the last week or so, Fred. So fantastic, and thank you so much. Let's move on to our next topic, Fred, and this headline has got me scratching my head. We're talking about intermediate black holes. Now, we've spoken about those before. There, up until recently, have been only 2 kinds found, little tiny ones, and others that are about, 55,000 times the mass of the sun or something, or maybe even bigger, some of them millions times bigger. Some of them as big as galaxies, as we talked about last week. But the ones that are middle-sized, the ones that are, somewhere around the 150 times the mass of the sun, are few and far between. And until recently, we didn't even know if they existed. Well, this headline, Fred, in Cosmos, reads, "Astronomers find Goldilocks black hole." Goldilocks black hole. What does that mean?
That's a really good question. It's not a headline I would have used. Goldilocks usually refers to things being not too cold and not too hot, but just right. But maybe it's a Goldilocks black hole because it has been, it's the sort of who has been sitting in my chair
right.
kind
Yeah,
of side
could
of Goldilocks,
be.
Maybe. But no, you're right that it is one of the puzzles of astronomy that we find what we call stellar mass black holes, which are up to about 100 times the mass of the sun, and the supermassive black holes, which start at something like 100,000 times the mass of the sun, probably usually bigger. Most of the ones we know about are millions of times the mass of the sun, and some are billions of times, like the one in M87 that was imaged by the Event Horizon Telescope. That's 6.5 billion times the mass of the sun. So there's this gap in the middle, the elusive intermediate mass black holes, as they're called. And there are a few suggestions of where these things might be found. There's some people have suggested they might be in the centres of what we call globular clusters. These are clusters of stars that we think are, they may be the remnants of the nuclei, the centres of some galaxies that our galaxy has gobbled up, smaller dwarf galaxies. But this field is still wide open. This story, though, relates to a probable detection of an intermediate mass black hole, and in fact its mass is right in the middle of that range. It's about 55,000 times the mass of the sun. That's the estimated mass. But it has been detected by gravitational lensing, which is a really neat trick that relativity allows us to do. When you've got a massive object in space, it distorts the space around it, and that can act as a lens, magnifying what you see beyond it. It's a way we study very, very distant clusters of galaxies. If a very distant cluster of galaxy has a nearer large cluster of galaxies in front of it, that nearer cluster will bend the space around it and act as a kind of natural telescope for the cluster beyond. It's a very, very powerful technique. But this story starts with something called a gamma ray burst. We haven't talked much about those recently, but they're thought to be basically the emission of a pulse of gamma rays, very short-lived, not as short as fast radio bursts, but short, seconds sort of length of time, They are thought to be basically the result of stars colliding. Stars basically annihilate, and you get these gamma rays. But they're short enough that if you had a gravitational lens and these pulses of gamma rays pass through it, you could find that you get two images of the gamma ray source because of the bending of the light. It's not a perfect lens. It can actually produce multiple images of the same object. And because it's a pulse that you're getting, you can look for the time delay between one arriving, one of the images arriving, and another one, whose light or whose gamma ray light has taken a different path through the gravitational lens. I'm not really explaining this very clearly.
So you're seeing the same thing twice at different intervals because of the disturbance to the space that it's travelling through.
Around the exactly that. And so what's happened is that by looking at the various quantities, and they are specifically how far apart the two images of this gamma ray pulse are, and what the time delay is in between them, the scientists who've done this work have been able to determine that they are seeing the effect of gravitational lensing around a black hole. But you can put the numbers into the into the formulae that relate to gravitational lensing to get out the mass of the black hole, and it turns out to be intermediate mass, 55,000 solar masses. Okay. And I might add as a footnote, Andrew, to this research, it comes from Australia. One of the authors is from Monash University, Eric Thrane, and Monash is a university in Melbourne that has actually a very, very strong school of theoretical astronomy in there. One of the theoreticians is somebody I know very well, John Lattanzio, and they do calculations about the way stars work and about the way that stars evolved. This is, I suspect, from the same group, but we're talking now about gravitational lenses, which is a remarkable science. So this could be the first really concrete evidence of an intermediate mass black hole being discovered by gravitational lensing, one of the curious freaks of relativity. It's a very, very nice story. And I'll shut up for a minute, but there is a postscript to it, which we might get to in a second.
No, I was just going to say it's interesting that they have perhaps discovered this through the observation of something else, by the sound of it. So an event that headed our way on two different paths, so we received the information at two different times, and the byproduct is, hang on a minute, the cause of that was an intermediate black hole.
Yes, that's right. It's exactly it. Yeah. So that's always very nice when something happens serendipitously and you get this a result that is something that you didn't expect. No. The postscript I mentioned is that one of the possibilities for the origin of intermediate black holes is that they may be primordial. That means they're remnants from the Big Bang. And the Big Bang remnants are not something that we've really got any proof of. It was suggested actually originally by Stephen Hawking many years ago that the Big Bang might have spawned many black holes ranging in size from tiny ones to what were they called? Slabs, I think, super large black holes.
That's
we
right.
talked about them a few weeks ago. They were also thought to be primordial black holes. So an intermediate mass black hole, because it's too big to have been formed by a single star turning into a supernova, but it's too small to be found at the centre of a galaxy, may well have been formed in the Big Bang itself. So they might be primordial ones. And in fact, one of the other side effects of this study that we're talking about, the one from Monash, is that maybe there are very large numbers of these black holes in our neighbourhood of the Milky Way. And of course, some people have suggested that Planet 9 is actually a primordial black hole. It's not a planet at all. It's something much more interesting, orbiting around the sun.
Anything's possible. And I suppose it sort of brings us back to that thing whereby we suspect certain things exist, but we've never found evidence of them. But ultimately, we probably will. And just like we suspect that life might be quite prolific in the universe, at least at a microbial level, intermediate black holes are probably quite prolific too. We just haven't been able to track them down as yet. That would be my theory.
Exactly. Exactly. That's pretty well sums up the view of astronomers, that these things are probably out there, but we're not finding them in anything like the numbers we might expect. And maybe it's because they're the fact that this thing has no evidence of any other anything bright surrounding it. All they know is that the signal from the gamma ray burst arrived by two different pathways, but there's nothing to see. That in itself suggests that you're not seeing something that's gobbling up material from its surrounding galaxy. You're seeing something that's perhaps just lurking in space, which is what you would expect primordial black holes to do. So it does kind of make sense.
Just hanging around on a street corner, doing drug deals, just minding its own business and hoping it doesn't get caught.
But it's been caught.
Indeed, and will go to court and will be sentenced. Yes, fascinating, very interesting, and hopefully more to learn about the elusive intermediate black hole. This is Space Nuts, the podcast. Andrew Dunkley here with Fred Watson.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.